despite the fact that we talked about last week how Mars became drier and drier as time went on. Drier and drier. That it lost its atmosphere.
Lost its atmosphere.
The
Liquid
volcanism
water's
died off.
died down loads, basically disappeared. Volcanism died down.
Mm-hmm.
It got a lot colder.
Yeah.
It's basically turned into a freezing desert now.
Yes. Yeah. Basically. And there are lots of things that kind of, if we look at the surface of Mars, if you just looked at the surface, yes, there's lots of evidence of old kind of water flows and things, but if you just went there now, you would assume there's definitely not life living here.
It doesn't. It's not a very nice place.
The extremes are really quite. They're not habitable environments. It's very cold. What's the temperature range?
I mean, it's a whole planet, obviously. So it's got a huge range,
Yeah,
but it's I think the average temperature is something like minus 50, minus 60.
Yeah.
And it goes down at night at the poles, minus 120,
and it goes up. Though.
It can go. I think at the equator, you can get. I think you can get temperatures of 15 degrees.
Yeah, positive temperatures.
Yeah. Sometimes. But most of the time is it's super, super cold.
Yeah. And because the atmosphere is so thin, any water that would exist there is gonna largely most of the time just boil off or sublimate away.
Yeah.
Straight to gas.
It's going to be
the
a race.
Very low. The pressure's very low.
Pressure very low. So it's if you poured some water on the surface of Mars, it'd be a race for it to freeze and evaporate. Both of those things would be happening at the same time.
Freezing and just disappearing off.
Yeah.
And it's covered in, obviously it's because it's got a very thin atmosphere and doesn't have a magnetic field. There's a hell of a lot of UV and nasty solar radiation coming in. Yeah. Just toning the surface.
Yeah. Just rinsing it.
Which is obviously really bad for things like DNA and biological molecules.
Isn't that thought to be why? I mean, that's why the surface of Mars is so highly oxidized and therefore red and stuff, right? Because it's just been savagely pummeled by.
Been irradiated over millions of years, billions of years.
Yeah.
And so those types of things. There's also lots of nasty chemicals on the surface of Mars, perchlorates, which we'll talk about a bit later, and other bits and bobs. That basically the surface is not a sort of place you would think to find life at all.
Yeah, even the most extreme, dry and cold places on the Earth.
You go to the Atacama, for example.
Atacama, which is in Chile.
Yeah, high altitude.
High altitude, super dry.
And you find perchlorate there, actually.
Yeah, you do. Yeah.
Which is...
we'll probably talk a bit more about perchlorate in a minute.
Yeah.
But yeah, you find it there, and it's so, and also the dry valleys in Antarctica, it's kind of they're again super dry, super cold. But even those places are really, compared to Mars, they're like a fucking oasis of
Well, we find life in those types of environments, don't we?
Yeah, we do.
You find really sort of drought-resistant microbes that are able to live for very, very long periods of time without water and can survive the being irradiated on the surface by the sun. Obviously, it's much more protected than it would be on Mars.
Yeah.
So there are organisms that can live in similar-ish environments, but that it's not. The problem with Mars is that it's consistently. It's consistently more extreme than those places. Whereas the places like the Atacama, obviously they have environments around them that are more habitable, which potentially blows in stuff, which the organisms there can use, and it has periods where it's not so extreme.
Yeah, that's the thing. You do get
mists and stuff.
You get mist, you get fog, you get just water vapor condenses out into. So you basically have these things that is these microorganisms that just basically spend most of their time dry down and not doing anything, and then a bit of water comes and they're like, oh sweet, and let's do our stuff, photosynthesize and everything else, and then and then go back into their dried down dormant state.
Exactly.
But if it was just constantly dry like Mars, I mean, well, for a start, liquid water that, without liquid water you can't have life. That's
no, as far as we know.
As far as we know, yeah. And the reason, I mean, it's because liquid water just promotes chemistry.
Yes.
It dissolves stuff, things bump into each other.
Yeah, it's a
and
solvent
undergo
for
reactions.
Lots of different speciation of chemicals.
Yeah.
Of carbon molecules, basically.
Yeah.
And other interactions.
Yeah.
But some of those organisms, you said they can live for very long periods of time, but eventually if they don't get a dose of water or nutrients or whatever, they won't be able to continually repair all the damage that's happening from the background radiation and stuff. So eventually they don't survive if they are sat in an environment that is
presumably,
and they can't grow in. Seemingly, that's
nobody's done an experiment that's long enough to actually get that.
No,
because like people live for a certain amount of time, and then that's that.
But you can do things like measure DNA damage over a shorter period of time.
Yeah, you can. That's
extrapolate that out and then you know how much damage it takes to make a DNA molecule useless.
Yeah.
And you can do that, measure that dose time, and how long it takes, and extrapolate out for a much longer period of time.
Yeah.
You can put the dose in much faster with a radiation source or whatever.
Yeah, that's very true.
So there are ways you can look at it, and the estimates are that things can potentially survive for hundreds of thousands, even millions of years potentially.
Yeah, I mean they've actually strapped some of these types of things to the outside of the space station, like literally just open to space.
Yeah.
Which is even harsher than Mars. I mean, there's no atmosphere; it's just full brunt of radiation.
Yeah.
Like hard vacuum, minus 200 degrees or whatever.
Yeah,
and
obviously
they don't live up there. They just sit there. When you bring them back, and you can actually revive them, and they live again.
Yeah, we got some of that stuff in our labs, haven't we? That
from the ISS. Yeah. It was a particular, because they've done a bunch of these experiments, and the ones that our lab's been involved with, like I think they took some rock from cliffs in Devon, south of England.
Yeah.
Shoved them on the outside of the ISS.
Yes.
And like, these rocks, they're just they're not even from like one of these desert places we were talking about.
No, cliff environments are fairly extreme.
They are fairly extreme. Yeah,
They tend to be quite dry, and a lot of water doesn't really sort of accumulate on them.
Yeah, when they do get water, it's like salty water that then dries down super quick.
Exactly. Yeah. So they're fairly extreme, but they're not like Atacama Desert.
Yeah. But anyway, so these things were stuck on the outside of the ISS, and then after like 2 years, was it?
Yeah, 2 years.
Brought back into the lab, and they're just in our lab. Like we've seen the things growing.
Yeah.
Like they're
we could have brought some
fine. Yeah, we should have brought some.
We're probably not allowed to do that.
No one would know.
Well, it would be on film.
Oh yeah.
Yeah.
Anyway. Yeah.
And they're perfectly fine after. So I think that particular strain, which was some kind of cyanobacteria.
Yes.
The top of the kind of like colony ended up burning. The surface got all destroyed, didn't
That's
it?
right.
And they preserved themselves by like a sacrificial layer of cells, I think.
Yeah.
It like caramelized on the outside, and then underneath that was. So
the actual ones that survived potentially weren't.
Exposed
were shielded
to space.
a bit. From the
like
super harsh radiation, at least.
And the insane pressures and stuff.
Like, I mean, I don't know. Pressure would probably be the same. Temperature would probably be similar. The radiation's like.
You might find the temperatures. Yeah, the radiation's
savage.
The temperature they can't have gone above 100, whatever their temperature tolerance of that organism is, though, it's not that high.
Yeah, that's true. I
think it's probably not, because it's space. There's not much conduction going on.
Yeah.
Maybe.
Yeah, although the temperature in full sunlight in space
is mad hot.
Pretty high.
Yeah. So I don't know how when they survived it. So they must not have got up to that temperature. And yeah, so I mean, these types of things are available. These bizarre organisms that can live in what seems like an uninhabitable place.
Yeah.
Like space is not a habitable environment.
No, and they can
these
survive
things obviously couldn't have like evolved there and lived there and stuff.
No, they
can survive exposures to it.
Yeah, they have like mechanisms of like dealing with stress that just happens to allow them to be able to do that. There's like that one. Deinococcus radiodurans,
which we also have in the lab.
Which we do have, we have a culture of that.
It stinks. The cultures of that
absolutely reeks.
The cultures of that smell.
So it was ages when there was one particular incubator that kept opening, and it was just like, it was like stink out the whole corridor.
Yeah, it's bright red Deinococcus.
Yeah,
it's like a very radiation resistant bacteria, and
it's like it's the most radiation resistant. No.
There's another one called like C. Gamma tolerans or something.
Right.
It was isolated from a hydrothermal vent, and it's like almost double the radiation resistance of Deinococcus. I think. I don't actually know. I'm pretty sure it's quite a lot higher anyway.
Yeah.
But yeah, the it's interesting because if you think about it, this is slightly off topic, but it's related. Where on Earth is a radiation-rich environment like that you would find in... They found Deinococcus from irradiating pork.
Yeah, it was like a tin of meat, wasn't it? Was it gamma radiation?
Yeah, trying to blast it with gamma rays.
Hitting it with gamma rays.
See if we can sterilize it. And
like, surely nothing can survive that.
Yeah, and then tried to grow stuff from the tin.
Yeah.
And something started growing. Turns out to be Deinococcus, which was quite happy with the radiation. But nothing on Earth produces radiation like that. There's no environment in which you'd have to consistently, to survive and to fill a niche, have to evolve such an extreme level of radiation resistance.
No.
Which makes it really interesting in terms of evolution as to how it actually evolved or why it evolved.
Yeah.
It's not. It's thought to be something to do with, I think, like oxidative. This could be. I don't want to get too boring, but it's basically
it's cool.
Kind of related to
either
a mixture of desiccation, like being too dry causes a similar type of stress in the cell.
Yeah, it's like causes just weirdly, like just basically through kind of coincidence, just causes the similar kind of damage that requires a similar kind of repair mechanism.
They both cause like what's called oxidative stress, which basically requires the similar repair mechanisms to be active.
Yeah.
So often organisms that are very resistant to being dried out for long periods of time are also resistant to doses of radiation.
Yeah, which is helpful for living in like a desert environment.
Yeah.
That's bathed in radiation.
Yes,
like
exactly.
Mars. Yeah. So anyway, so we kind of established that there's organisms that live on the Earth that could probably survive all of the extremes on the surface of Mars.
Yes.
So low pressure, obviously, again, is not a thing that you find like on the surface of the Earth, but like just by like exposing stuff to the space conditions, which is like more extreme pressure, than Mars. We know that that's something you can survive, like temperature, obviously, like radiation, whatever. But the problem is surviving it isn't enough. Like for stuff to actually live there, it needs liquid water.
Yes.
As
to multiply and
to do anything.
Yeah.
Otherwise, it's just
sitting there
dead bit of organics. Yeah. Essentially, just a dead shell of nothing without water.
Yeah. It's almost like a sort of seed or something. Like a seed to a tree. It's just sat there doing nothing until it gets the right conditions in which it can germinate. Sort of. It's a bit similar.
Yeah.
But so you just said that we established there are things that can live on the surface of Mars, but they have to wait a certain period. They have to be able to have access to water
like
or a habitable environment at some point.
Yeah, this is the crucial thing, and this is why like NASA's Mars exploration program is follow the water. Like that's like the driving thing, is because we can find all these things that survive all the combinations of extremes. So the limiting thing seems to be access to water. Mm-hmm. In the same way that it is in super dry deserts on Earth.
Yeah.
Defines everything.
Yes, yeah.
So if we want to know if modern Mars has life or could potentially have life on it, we need to look for liquid water. Yeah.
And there's been some stuff in the news. Was it recently? It was about
Definitely
a year ago,
within the last year, yeah.
Half a year ago. About, and they've been suspected for a long time to be related to water. These recurring slope lineae, so these features that appear seasonally on Mars. They appear. There seems to be like what looks like flows down the sides of crater walls. And they suspect that they may be related to water flowing from something on the surface of Mars.
Just because of the shape of them and the way that they form, like it just looks like a flow, like a liquid flow. Obviously, like loads of people who are challenging that and stuff, because you can't just assume that's what it is, obviously.
No.
But it was like a bunch of pictures coming back from this camera called HiRISE, which is on the Mars Reconnaissance Orbiter, and like if you haven't done this before, you should go check out the HiRISE.
Well,
website.
we'll do a. You should, and we will do a video.
Yeah, we'll do a
tour of Mars video. We'll bring in a load of HiRISE images.
Yeah, but there's just some amazing pictures on there.
Yeah,
like fucking
really
millions.
very very high resolution images of the surface of Mars and these different surface features that are potentially water forms. So.
Yeah, and it actually might, some people might not appreciate like quite how like diverse and stunning the surface of Mars looks. So like check them out. It's a whole planet like the Earth, it's got. Anyway, this is a bit of a tangent, but anyway. So HiRISE was taking a bunch of images and found these like dark streaks, as you were saying, that gradually like get longer and longer and longer. And I think the crucial thing is that they form at particular times of year.
Yes, and on certain sides of certain like craters and things. The north side or the south side, I forget which one.
Yeah, I think they're normally like equator facing, possibly.
Yeah, something like that. From both sides. Something like that. I can't remember exactly, but they form on one side, And so it's related presumably to, because it's seasonal and because it's one side of it, one gets more sun or whatever, and you end up with presuming that there's a melting effect occurring, or some kind of atmospheric condensation effect occurring that's producing enough water to cause a flow down the side of these craters, which, that's what types of organisms on Earth would be potentially loving.
Yeah, exactly.
In these types of environments.
Yeah, like
that's what that could be necessary for them to survive. So
it goes from Mars seeming just like a totally cold, barren desert to something that actually has like a process going on.
Yeah.
With involving liquid water, potentially.
And
now,
so for example, when you were talking about the Atacama and the mists, that's a very similar analogy.
Yeah.
In that seasonally you get maybe mists coming in, which deposit some condensation and things on the ground that the organisms can then use as a source of water.
Yeah.
A similar thing could be potentially happening on the surface of Mars.
So they reckon that these things are coming from either a underground source of water, like an aquifer or something, and it's just like upwelling. Or from the atmosphere. So either like a mist situation, or which is actually something that happens in the dry valleys in Antarctica. You actually get like water vapor condensing out directly into salts, basically. So if you ever have like salt that you keep like in your kitchen or whatever, and it goes like a bit clumpy after a while, it's like, oh, like it's useless now. I can't get it out.
Yeah.
Like it's basically that. Like it's taking water from the atmosphere to a point where it actually turns into a liquid like brine.
Yes.
And so those are the two scenarios. And because of these things are happening way up on the sides of these hills, it seems kind of unlikely that they're from like a deep aquifer, because you'd expect to see them coming out where like a hill like intersects an aquifer rather than like way up at the top of it.
Yes, although there is that doesn't necessarily preclude that. If there's a say a highly permeable layer of rock,
could like wick up.
That wicks up, and you potentially have less permeable layers around it. It kind of gets forced up in these particular regions. Obviously that only holds for a certain amount of time. You can't have that happening in like every crater over Mars, because it just statistically is not likely to be forming in those. The fact that it forms in these particular levels of certain craters and things, and they're sort of consistent, suggests that that's probably not what's happening.
Probably not.
And there was a study that it was done at NASA, wasn't it? It was a NASA study.
Yeah.
Of the spectral features of some of these slope lineae, or whatever you want to call
RSL.
it.
It's a really like tedious acronym.
Yeah.
Recurring slope lineae.
Yeah. And they found in the dried deposits, or was it the flow itself?
The
remains.
The flows themselves. I mean, I think the problem was these things are tiny, and
really tiny.
The instruments on the orbiters like just can't get enough resolution. Like the pixel size of the instrument is like huge, so they have to do all this like crazy like data processing stuff to average out and blah 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 blah. But I think they have yet to detect like a water signal from them. But but what they have detected is like essentially the salts that you would expect if these things are like condensing out the atmosphere, like I was just saying.
Yes. So that's when we were talking earlier about perchlorates. That's the salt they detected. Perchlorate is just a nasty. It's nasty. It's like rocket fuel.
It's used in rocket fuel, or in some types of rocket fuel as an oxidizer.
Yes, exactly.
It's super toxic.
Yeah, it's very toxic to us. If you burn it, put a flame on a pile of perchlorate, it will go up.
Yeah.
And yeah,
we've got some of that in the lab as well.
We have. It's very safely kept.
Yeah.
Well, it is.
No, it is. Yeah, definitely.
So you've got we said earlier we found perchlorates in certain environments on Earth, and actually, the Phoenix mission found perchlorates
on the surface of
Mars. And that kind of changed some of the sort of paradigms, I suppose, that existed in Mars exploration before, because we didn't really normally expected perchlorates.
No,
when that thing landed.
I think before that, like perchlorates were thought to be essentially only like a synthetic contaminant, like something that we'd made on Earth.
Yes.
And then the fact that we discovered them on Mars made people sort of reassess that.
Yeah.
And now we know that they're basically produced in the atmosphere.
Yeah.
Again, through radiation.
It has to be very, very dry environments.
Yeah, but that's the thing. They're like super soluble, and biology on Earth like uses them and all kinds of shit. Yeah. So in anywhere that there's any kind of like rainfall at all, that you don't find them, because they fall out of the atmosphere, but then they're just immediately like solubilized and gone. But in like the Atacama and the dry valleys, you get like a gradual accumulation of them.
Very low levels,
which is essentially what's happening on Mars.
Yeah, and they found like we said, they found a signature of perchlorates at the end of one of these RSL things. Now, if that is a perchlorate brine, so if it's absorbed moisture from the atmosphere and is essentially a concentrated perchlorate brine, most scientists, and we agree with this because we do actually do some work related to this stuff. It's probably not.
There's not going to be
pleasant
life there
for life.
No.
It's probably going to be essentially a perchlorate brine is a very extreme liquid system.
It's liquid in the sense that it's like
there's water.
It will flow downhill, and so it's liquid. It's a liquid thing.
Yes.
But like it's not the kind of liquid you could do biology with.
And this is one of the faults of the follow the water thing, is that not every water body is habitable.
Yeah.
And a saturated perchlorate brine.
Yeah.
Nothing going to be living in that.
No. So this is the thing, like we were saying earlier, pure water on Mars will just evaporate or freeze straight away. Yeah. Having a super salty perchlorate brine means that neither of those things would happen so quickly. Yeah. Like it slows down, it lowers the freezing point and all this stuff. Yeah. But the actual conditions there are still the same, and essentially what you end up with is like a brine that's so ridiculously concentrated that like nothing else will basically dissolve into it. Yeah. No biology, at least.
No, exactly. There's no water sort of available.
Exactly. It's almost like a liquid mineral.
Yes, sort of. Well, sort of, yeah.
I mean, very, very...
I know what you mean.
That's an analogy rather than an actual
the water's all been taken up, basically, by the perchlorate that's dissolved in there.
Yeah.
And only certain types of like salts and things can do that, but perchlorate's one of them.
Yeah. So
it's also super toxic as well.
Yeah, well, that small little hurdle to get over. But that's the weird thing, is like at the same time that when that paper came out about the perchlorate detection in these streaks, there was like the completely opposite reaction. So the media were like, water's been discovered on Mars today, liquid water's been discovered on Mars, this is amazing, like it's probably habitable, blah 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 blah. And like scientists, like planetary scientists, were like, oh shit, that's not habitable.
Yeah, as soon as you found it was perchlorate, exactly. There was a confirmation that it was brine. That it was, a liquid water thing. Yeah. And everyone was like, what was that? How do they find that out? If you read the papers or read more into the news articles. Oh, it's from perchlorate salts. Straight away.
Because that means it's coming from the atmosphere, and that means it's probably, not very nice. No. If it was coming from an aquifer underground, then that could be a totally different story, but it doesn't seem to be.
Yeah. So I would, the water on the surface of Mars from those things is not good news for the habitability, the positive habitability of the surface of modern Mars, really.
So let's say there were some of these like crazy drought-resistant, radiation-resistant things dormant in the soil where one of these things flowed over them. When it flowed over them, it wouldn't wake them up, and it wouldn't allow them to then go on and do stuff.
No, it might even kill them.
It might even kill them, yeah. So Mars has probably been in this sort of state, like super cold, super dry, with maybe these like flows of perchlorates or whatever, for fucking ages. Like the Amazon, we were talking about last week, like the Amazonian has been the last 3 billion years, and it's sort of been a bit like this.
Yeah, it's just got worse. It's just got, it's been getting more like this for those 3 billion years, and has been probably in its recognisable kind of state that we now know it in for a long time. Yeah.
But there are times during that period that it could have been slightly less like horrendous.
Yes.
Than it seems to be most of the time.
In its recent history.
Yeah, in its very recent history, and the reason for that is that unlike the Earth, Mars wobbles back and forth shitloads on its axis. Yeah. So it's called its obliquity, basically, which just relates to like the angle of spin, like in relation to the sun. So the Earth is like tilted about sort of 21 degrees, 22 degrees, something like that. And it stays basically at that angle because of the moon stabilizes it. That big old moon. Yeah. Whereas Mars doesn't have a big old moon. So it just wobbles all over the place. Yes. I think it's something like every 120,000 years. Yeah. It's gradually moving between like 15 and 35 degrees. And that essentially totally messes with the climate.
Yes. So is it constantly moving, or does it go through phases where it suddenly goes more and then
I think it's constantly moving. Yeah. It's constantly. It just so happens that right now it's at a very similar angle to the Earth, but that's just coincidence that we just started looking at it at that time. But I think it's constantly moving. It's like processing.
Yeah. Yeah.
I mean, obviously nobody really knows. We haven't watched it for 120,000 years.
No, sure, but that's all based off modelling and some surface evidence, right? That things have changed.
That's right. Yeah. So that's the crazy thing is that I mean, on Earth, like a 1 degree change in obliquity, like I think something like 40,000 years ago, something like huge amounts of glaciation, like change, like temperature changes, huge.
Sometimes they're called Milankovitch cycles,
right?
I think.
So on Mars, it's much more extreme.
Yeah.
And like the polar ice caps on Mars, which are like a shitload of CO2 ice.
Yes.
All like sublimated
with water
the
ice
atmosphere.
on top, right?
Yeah.
No, wait, is it the other way around?
The other way around, I think.
So it's a big water ice cap, and then a seasonal CO2 cap.
Seasonal CO2.
Yeah.
So all of that ends up in the atmosphere, and like the water ice is thought to be redistributed like into lower latitudes, and I think that people think that there's melt happening, like so that because obviously all the CO2 goes into the atmosphere.
Yeah.
It's higher pressure. You can have liquid water. Doesn't boil off so easily.
Yeah.
I don't know. I mean, it's not just suddenly like turns into the Earth.
No.
But basically, I think through people's calculations, they reckon that you can get some melting at like mid latitudes or low latitudes near the equator.
Right. Okay.
Yeah, just because of the distribution of heat and stuff.
And that produces these things called gullies, right?
Yeah, potentially. Everything kind of correlates at the right time.
Yes.
Like gullies are just like mini valleys, I guess,
that form in a similar way, but they're bigger and they form around craters and high like regions of high topography and these types of
people
things,
reckon
right?
they form by water.
They're deeper, sort of almost V-shaped kind of streaks that kind of or small valleys that appear at the sides of these craters, and they seem to be relict now in the sense that they're not actively being formed. But haven't been like lithified and buried and stuff, so like turned into rock. But they're all over Mars, aren't they?
They are. There's shitloads of them. Yeah.
Different latitudes and stuff.
Yeah.
And so they may potentially be related to these times when we have this redistribution of water and this change in the thickness of the atmosphere. And therefore, in kind of relatively recent history,
within the last 100,000 years, probably.
Yeah, which is recent in terms of geological time. But
super
that's not
recent in terms of geological time.
Yeah.
But I mean,
it's not
obviously
really,
not for us. It's not recent.
No,
we have to wait another 100,000 years for it to happen again. It would be like, oh, for Christ's sake, hurry up.
So relatively recent in terms of geological time, and in terms of it's a long time for microbes, but there's some potential that some microbes could live between these cycles, right?
Well, I mean, if it
survive 100,000 years, in a sort of state in stasis, underneath the surface, slightly underneath the surface, they're blocked from radiation and
I mean, presumably like this kind of wobbling has been going on throughout the whole of Mars's history.
Yeah.
So if there was like a biosphere way back in the Noachian when it was all like happy and warm and stuff,
it would have evolved.
There would have been like a strong selection pressure for it to have adapted to these cycles as it got drier and drier and drier and drier. So I mean, it's possible, I guess, that when you have a bit more like liquid water happening, and it's not. I mean, again, like it's not going to be these high obliquity things aren't going to turn it into the Earth, but it's almost like it could push some regions of it into what we see in like the Atacama or something.
Yes.
So like there are areas that maybe have like transient liquid water that could be used by surface bugs to grow.